Good afternoon, everybody. My name is Dave Voutila. I'm here to talk to you about graphs for cybersecurity. I'm a field sales or solution engineer, depending on the day of the week, with Neo4j. You can reach me at my private blog at sisu.io or via email at davevoutila@neo4j.com. And I'm also on LinkedIn, like everybody else. This is myself and my dog. I'm from Neo4j. If you haven't figured that out by now, we are the graph company. We're the largest dedicated investment in graph technology. We've got over 300 employees. We're headquartered in the San Francisco Bay Area, and we've got a variety of Fortune 500 customers using us across the board for a variety of different use cases, including cybersecurity. So let's talk about cybersecurity. Usually when people mention cybersecurity or give a talk on it, they always include some sort of hokey little stock photo of a hacker, usually someone in a black hoodie like myself, with it up over their head in the dark, hammering away at a keyboard, pretending to steal your credit card. Reality is, usually what we're talking about is something like Evil Corp. This is a alleged member of Evil Corp. This is a group from Russia that is allegedly behind the recent Garmin data breach, ransomware attack, where Garmin allegedly, I believe, paid tens of millions of dollars in a ransom to get their data back. Who knows? They've also found a way to steal hundreds of millions of dollars from various financial institutions around the world, as is evidenced by the stack of cash in this person's lap. And how big a problem is this? Clearly, Evil Corp is doing well. The average cost of a data breach is probably much higher than you think. So in the United States, it's about 12.2 million Canadian. Canada is 6.3. And probably the scariest number is it takes over 200 days to identify a data breach has occurred. This is all data coming from IBM's research teams. The most targeted and most expensively hit industry is financial services in Canada, which is another reason to be concerned. On the bright side, at least Canada seems to be doing better than the US, cost being about half, and a little bit faster to identify and respond. So silver linings. The reality, though, is the deck is still stacked against you. Graphs are part of that reason. Defenders, companies, we all like to think in lists. We like to think in silos. You probably have heard all about silo problems from every vendor under the sun. The reality is attackers are thinking in graphs. They're thinking in lateral, horizontal movement throughout your organization. Get a toehold, find their way in to get what they need to get to the crown jewels. And what does that look like in practice? So even an exploit looks like a graph. This is a visualization of a remote code execution found in WinRAR, as documented by Microsoft's research team. I mean, it is a graph, starting with a spear phishing email in the upper left, showing you how they can get all the way to local code execution and exploitation via a Dropbox payload in the bottom. But that's how graphs are being used against you. But how can you use graphs to defend and to manage your risk? So the key is a holistic view. In order to create a holistic view, you need connected data, and a graph is all about connected data. You want to be able to identify the risks to your assets and business processes, and ultimately know how to protect those systems, services, and ideally the crown jewels. Not just from a pure compliance standpoint, which we all must comply with typically in the financial services at least. You need to do it in practice because the penalties of a ransomware attack are quite high. You also need to be able to detect anomalies when they occur and be able to respond rapidly with confidence. You need all the information at your fingertips. You can't be working in silos with each team having their own tool with their own view. You really need a single source of truth. That's what the graph gives you. Because traditional databases are only designed to store and retrieve data, which is good if you build a big enough database. So people built big data technology, which is good if you're just trying to aggregate and filter data. But the reality is you need to be able to connect your data. So this is data you already have, and this is all about exploiting how it connects and fits together. And that's what Neo4j is all about. We provide a single platform. The Neo4j Graph technology encompasses everything from data onboarding and integration all the way through to discovery and visual analytics, with both graph data science and analytics and machine learning in the middle, as well as the ability to build custom applications that provide graph transactions as well. All while not losing your data with true ACID semantics and the ability to scale to handle any particular data loads. But enough talking. Let's get into a demo and I can show you how it works. So in this particular demonstration, This is all derived from a very common need in the industry, which is Windows domain auditing. So taking a look at your Windows network environment, which pretty much every enterprise has, whether you're a Windows user or not, and looking at how the users, the groups, the assets like computers in the network, all in a domain, kind of interact together through permissions. So this is sort of an IAM auditing use case. So since we're talking about Windows domain auditing, what I want to demonstrate today is how graphs are a natural fit for this use case. If you know anything about Windows Active Directory, it's a very hierarchical system. Groups can be memberships of, have memberships with other groups. By being in one group, you might be inheriting permissions from other groups. It's just a hierarchy. And whenever you see a hierarchy in nature, it's really a graph staring back at you in the face. And what I want to show you today is how you can use graph data science techniques to not only identify, but assess and measure the exposure and risk that your environment poses currently, and find those critical weak points. So first, we're going to take a visual approach. I'm going to walk you through how to identify things at a high level, and then we'll dive in and take a look at, from behind the scenes, how do you get to that point where you're making it easy for an analyst to sit down and visually identify what's of interest and be able to drill in rapidly to figure out what they need to investigate. So let's get into the demo before we talk about next steps. This is our Neo4j Bloom product. Bloom allows us to use natural language search to retrieve data from the graph. So you can start with something open-ended. Let's say everyone that has remote desktop access in a particular Windows domain. We've got this testlab.local domain. These are all of our users and groups and computers they have access to within our network. See this beautiful virus-looking thing here on the left with some scattered connected nodes here on the right. On the right-hand side, what you're seeing is an overview of what's in the scene. We see a total of each node type. So we have 902 computers accounted for in here, 277 groups, 353 users in our scene, as it's called. We can zoom in and investigate individual nodes. See, here's a user. We've got an icon and nice color green for them. They have CAN RDP rights to be able to remote desktop into these two systems in question. If I double click on one, we can investigate some properties about them. So we can see their Windows object ID and their account name. You'll notice I've got a variety of colors here. We're going to talk a little bit more about what these represent, and I'll show you how I put this together. But first, let's take an example. Let's take a look at a particular user. Maybe we need to look at a user account and understand what permissions they might have. So maybe we're trying to figure out who or what systems a particular user, this one I know is named Henrietta, what can they access through their RDP rights? Well, if you take a look at the user in Active Directory, you can see maybe 3 explicit permissions where they can get to these 3 servers in our environments. Pretty simple. You don't need a graph for this. I'm not trying to kid you here. But what about all of the groups that this person is a part of? Let's add their groups into this scene here. So I'm going to use a query for all their group memberships. Okay, so it looks like they've got, if we look on the right, Henrietta here is a member of 12 different groups. And you can see a couple of them are members of other groups. So they might be inheriting permissions from this hierarchy all the way up this chain. So let's see, are they inheriting any other remote desktop rights? Let's take a look at any remote desktop access they might be getting through their group memberships. So when we account for inheritance and we traverse the graph and unravel this hierarchy, you can see our computer count, which was 2 or 3. I'm really bad at remembering things. I should have written it down. Is all the way up to 17 now. So pretty much almost an order of magnitude increase here. Pretty upsetting depending on what you were expecting for this particular user account. But this is just one piece of the puzzle. So this is assuming, maybe this person is being, good, not a malicious actor, and we're just trying to understand what systems they can get onto. But if this account were to be compromised, attackers don't play by the rules. If an account has access to a system via remote desktop, yeah, they can leverage it. But they don't need remote desktop in order to be able to move laterally through your organization. So let's take a look at maybe the other remote abilities that this particular account might have explicitly granted to them. So I'm going to add these in, and let's zoom in and take a look, and I'll explain here. You'll see we've got these two new relationships in the scene. I toggle my scene filter here. We had this remote desktop permission, but now we've got execute decom. And this is one of these Windows protocols that allows you to do distributed com. If you're curious about it, feel free to Google it. I recommend Googling decom remote code exploits. There's a lot documented online. Net, this could allow a malicious actor, in this case, this particular account, to very easily move laterally through this environment, even to systems that they don't necessarily have remote access to via remote desktop. But this is just their direct permissions. So let's add in those groups again and see just how bad this could be. So let's look at all the remote abilities for our user, add these in, and zoom out a little, and you'll see that we've gone from our, what was it, like 2 or 3 systems up to maybe 34. So that's really the total impact that very easily somebody who gets a hold of this account could have on our network. But getting access to just the computers is one thing. I mean, if it's a domain controller, that's really game over. You might as well start looking for another job if your job is to prevent that, because you're going to have a very bad day. Or if it's a database full of, personally identifiable information or something else that shouldn't be falling into the hands of somebody, either they're going to take it or they're going to lock it down and give you a ransomware attack that's going to cost you millions of dollars. The way they could be doing this, though, is targeting other users in your environment. Instead of just getting on a box, maybe they're looking for somebody with domain admin rights, really one of the other holy grails. So really, who could this particular account reach out and touch? If we think about it, each one of these systems could be a server. Each one of these servers could have some other user on it, assuming, maybe someone else is doing maintenance on the machine, maybe somebody's working on it for some reason. At any given time, somebody else could be logged onto a machine that this Henrietta individual, Henrietta hacker, might be able to reach out and exploit. Let's see how bad this could be. So let's see who could this given user impact. So using Neo4j and the traversal capabilities of the product, we can just follow this web all the way to the endpoint. If we zoom out a little bit, you'll see all of these green nodes. These are new users that have been added into our scene. So there's over 47 now. If we zoom in, you'll see each one of these that's been added is related to this, each individual computer via these has sessions. So they might be logged in remotely or locally onto these boxes. The reality of Windows networking, and quite frankly, it's not really a Microsoft thing. If you have local admin or root access on a machine, somebody else is logged into it, chances are there's numerous attacks you could do in order to gain access to their credentials, whether it's getting their password on Windows through something like Mimikatz or some other attacks on memory on a local machine. Heaven forbid this thing is hosting other virtualized hosts, and somebody would be able to really do some damage. So we've gone from the single possible account, which I believe this one right here was Henrietta. Yep. And this is really the scope of impact that they could have very quickly if somebody knew what they were doing and was able to get this account into their hands. But this didn't really answer the question as to, are they getting domain admin? So let's use Bloom again, and we'll just say, okay, let's look for any user. We'll look for a user node that is a member of maybe the domain admins group. Let's add these into our scene. Zoom out here. So the good news is, if we look at our new little cluster here, this is our domain admins group. For our domain, testlab.local, these are all immediate members of it. I don't believe there are any groups actually that are, if we take a look and we inspect this particular node, and we look at its neighbors, they're all users or computers. The relationships coming out of here are admin2 computers or member of. So nicely, we haven't done any weird nesting, putting groups within groups that roll up to domain admin, which would be harder to track. So the good news is there's no connection. We can very visually identify, okay, at least you could maybe ring fence this environment. None of these domain admins are logged onto these machines. You know, it might not be that bad. That's the good news. But how would we know this in practice? How would we know to look even at this particular account in question? Obviously, this is a demo, so I knew to look at it because it was interesting. But how did I even find it? There's ways you can identify connections in your network just visually like we're doing now. But more importantly, you can do this behind the scenes using our graph data science techniques, using different algorithms around centrality scoring, community detection, and other ways of measuring the importance and the connectivity between systems, services, and people in your network. So let's take a look behind the scenes at what this looks like. I'll give you a little preview first. And what we're going to do is take a look just at our computers now. So let's say we want to look at computers that have some sort of allowed to delegate. So maybe these are services that are running that have permissions in the Windows world to be able to delegate on behalf of another machine or act as another machine or service. If I zoom out, this is essentially our, we got 1,200 computers in our network. You'll see we've got these nice little bright dots. There's a nice bright red one right here. And if I zoom in, we'll see this thing we can call a graph component, which is really a collection of nodes or vertices that are connected through edges, or in Neo4j parlance, relationships. This one in the middle here has a PageRank score. So I use the graph data science library to measure this quantitatively and understand at a global view how to identify this node based off of the fact it connects to more machines than others. If we take a look, you can see these allowed to delegate relationships. So let's see how I got to this point. We take a look at Neo4j Browser. This allows us to run queries directly against the database. We were just using Neo4j Bloom, nice visual discovery interface, natural language interface for analysts to use. This is what more developers or database administrators would be using to interrogate the database directly using the Cypher query language. And let's say we want to run PageRank on these computers. So we already saw in Bloom, we have this allowed to delegate relationship that connects machine to machine in our environment and makes a nice, what we call a monopartite graph. We have computers connected to computers through common relationship types. That's really all you need for a PageRank type algorithm. Using the graph data science library and its stored procedures, it's as simple as a couple lines of Cypher here. So we call the algorithm gds.pagerank using the streaming variation, which is just going to stream results back, just like I'm writing a SQL query against my relational database. I'm giving it some parameters. So we're using what's called projections here. So graph data science is going to look at all our computer nodes, anything with a computer label in our database, projected into memory for analysis. It's going to use the allowed to delegate relationship, and it's actually going to flip it for us because of the way the arrows were on these lines. We need to make them go in reverse. So we can do that at projection time very easily. And then we're just going to aggregate and sort based off of their score to try to find the top 50 most connected or most influential computers based off of these relationships all around allowed to delegate. So if we take a look, we've got comp 03760, comp quad 04. They have pretty high scores. The scores tail off as we scroll down. We get a nice long tail. And if we pan back over to Zoom or to Bloom very quickly, oh, look at that, 03760, our high score from PageRank. Now, how did I make this change? In Bloom, you can also apply rule-based styling. So if I select our computer nodes here on the right, I can apply rule-based styling, in this case, based off of the PageRank score. I'm giving it a range of numeric values and different gradients for shading. And I can also scale up the size of the node. So that way, as a visual analyst, I get to reap the benefits of the fact that somebody else did the work analyzing the data for me. Now I just apply my human intuition to say what looks weird or outstanding here. Like, I can very visually identify this graph component over here. I can see that this person is red, or this machine rather. Actually, it is a person, which is interesting. And they're connected to these others via allowed to delegate relationships. Apparently, I didn't filter out the users here, but that's interesting to know. That's one approach you can take. Now, a common use case in cybersecurity, especially for folks managing just a Windows domain or even any cloud identity access management environment, is to routinely audit for either users that have too many permissions, users that have permissions that don't look right. So like really it can become sort of subjective. There's ways to put rules in place. So like if you use Google Cloud Platform, which I use quite extensively, pretty good at telling you when you've given too many permissions based off of what it's seeing used. But, that's for some definition of used, because if the users are using those permissions, maybe they shouldn't be using those permissions to begin with. So let's take a look at how we can analyze the users that are in our environment. So we're going to use the Graph Data Science library again. Why not? This time we're going to use something called node similarity. So let's say we want to look at all our individual users, and we want to use their remote access permissions to different computers in our network as a way to find who's similar to who. So if I can connect to a machine and you can connect to the same machine, we're pretty similar in nature. We must have at least some common permissions overlapping. Based off of the number of machines that we share in common, you could say we're either more or less alike. That's exactly what we're going to do here. In this case, we're going to use the Cypher query language to more intelligently match the components of our graph. We're going to project into memory all the users and computers. We're going to create what's called a Bipartite Graph, two different types of nodes. And what we want to look at is similar to what I showed you earlier when we looked and unraveled all those remote desktop permissions. For every user, traverse a path out from that user node through any of their group memberships, more specifically to any computer through the CAN RDP relationship. So this is going to create that, that tree structure from each user that we were doing in Bloom. We're going to use that output as the relationships, basically the user and the endpoint of the computer. We're going to create a virtual edge between them in memory in Graph Data Science library. That's where we're going to run the algorithm. Out pops pairs of nodes and a similarity score. So we'll have just a little cutoff, sort by the score, grab the top 50 so we don't have to wade through every possible pair and combination. If we take a look at running this query, you'll see we've got a table here where you see these reciprocating pairs, Ahinzi and Keichelberger, and then you'll see them repeated down below. If I'm similar to you, the implication is you're similar to me with this particular algorithm. And we can see their score on the right-hand side. So we've got some users that are definitely more alike than others. Now, if we wanted to, we could adapt our algorithm, use different permissions here, add some, subtract some. Right now, we're just focusing on remote desktop access for the sake of this demonstration. This is just giving us the results. So how did I get from this table of results to that styling in Bloom? Well, nice thing is each algorithm in Graph Data Science has another variation called write that will just materialize these results directly back into the underlying database. So this query changed only subtly. You might notice the difference, you might not. Same node query, same relationship query. But now we're going to say, let's create an edge directly between each user and each computer. Let's call it similar by RDP, similar by their remote desktop permissions. And since node similarity gives you a score, some sort of weighting as to how similar something is, let's stick it as a property on that relationship, right on the edge. Now, when we run this, we'll get some summary stats back. It just wrote 3,300 relationships to our database, looking at over 350 users. Not every user was applicable because maybe there was no overlap or maybe they didn't have remote desktop permissions, which is totally possible. Now, if we take a look at our database schema, and let's say we preview the similar by RDP, I've actually duplicated some of the results here, but you'll get the general gist. We've got users, which are these green nodes, connected to other green nodes by a similar by RDP relationship type with a score. So while I've run this multiple times, the beauty is I'm getting the exact same score out. Very deterministic. So that relates users to users. And if we pause for a moment and we look in Bloom and we try to make some sense of this, what we're going to see isn't too helpful yet, to be quite honest. We want a user similar to, by RDP, any other user. And so you might be thinking, okay, well, we're at that point in the demo. Time's almost up. It's going to be some nice, beautiful little visualization. And instead, we get this really nasty rat's nest here. Because it turns out there's so much overlap in our network that just showing if somebody's similar to any individual isn't really that helpful. This is useful in certain applications for doing things like recommendations, like given one user, can we find a similar one? Given one product that's been purchased with others, could we recommend one of those other products? Those types of things. But what we really need to do now is really pick apart this mess. So let's do that using a different algorithm, and we're going to create communities based off of connections between these users. So the last query we're going to run applies the Louvain modularity algorithm. So similar to what we just did, we're going to target nodes in our graph. In this case, we're going to look at just users, because all we care about are users similar to others. So grab all the users in our database, grab any edge between them, any relationship type called similar by RDP, the one we just created, with the source and a target from one end to the other, and we're going to keep the score property from the relationship that we made just previously. We're going to use that score as a weight. Louvain takes a weight in order to determine community assignments. Out pops a community ID and a node ID. And then similar to what we did with those similarity outputs, we're going to just aggregate those, bucket them, and take a look at their sizes, and just do a little bit of filtering of the noise, because who cares about a community of one? Pretty boring and lonely. You'll see we get 11 results. So we've got 11 communities that range in size from 16 to 53, roughly. Well, exactly. I guess it depends on if your vision is good enough to see that's 53 or 52. Each one of these corresponds to the internal ID of a user in our database. So what we can do is back reference this to their actual identifier in Active Directory or their user account name. But most importantly, what you can do is also connect these together to help visualize them, either through applying the community ID property, which I've already done for you, or connecting an edge between them to help facilitate Bloom visualization. So if we clear our scene, we take one last look, and let's say we want to see all the communities. I've got a nice pre-canned query here for the end. This is that same rat's nest, 336 users. Using the same community IDs, I just connected members to each member in some sort of chain, just as a way to tie them together into graph components. And then using Bloom's rule-based styling, applied the Louvain community ID, some coloring to give it that nice visual pop so you can visually identify, okay, this is a different graph component or community from this other one. Now we could say, let's look at what really makes these folks common with each other. What are the common systems, permissions? Are there really a lot of group overlaps? If we had multiple domains here, it would be interesting to see if there's something going on cross-domain. But this is just showing you a couple different steps you can take as a way to dig in, especially at a holistic global level, and not just looking at each individual user account, which you could be doing until the end of time. So to recap, we took a look at a database derived from Windows Active Directory. We essentially performed a user-based audit. So from a particular user account, what could the impact be in terms of how far could their tendrils go out if they were to become malicious or compromised, whether directly through their current remote desktop permissions or indirectly through remote code exploitable permissions that would make it very easy to move horizontally. And then also what users could be impacted based off of who was on those target machines. Then we took a step back. We looked at how you can do this holistically at a global level using graph data science techniques, and was able to piece together a beautiful visualization of common users that have common permissions that may or may not even be within the same groups in your environment. But just because of certain end results, the machines they can connect to, they have some commonality between them. And with that, that's the end of our demo today. And for next steps, I recommend if you have any questions about graph databases, how they work, how you can leverage them, you go to neo4j.com and you grab this copy of Graph Databases for Dummies that we're providing today to all attendees. You can also go to neo4j.com/download and grab a copy of Neo4j Desktop, which was the platform I was using to demonstrate to you the Windows domain auditing today. If you'd like, you can also reach out to me afterwards and I can give you the data set. Feel free to also stop by our virtual booth, ask any questions you want with our graph experts. More importantly, we've got a great session from Bank of Montreal speaking about knowledge graphs using Neo4j in financial institutions at September 30th at 2:30 p.m. And feel free to book a one-on-one. Ask us any questions you want, bring your problems. We can show you how a graph can solve them. So any questions, want to get access to the data, the demo, feel free to reach out, dave.voutila@neo4j.com. Thanks again.